Welcome to another topic of metrology and instrumentation. Today we are going to concentrate on methods of least squares and regression analysis. As such, I'm going to cover regression analysis and I'm going to also be talking about quadratic regression analysis and how we can actually perform a regression for a nonlinear function. So let's talk a little bit about methods of least squares. Suppose that we have a set of observations. Remember, this is related to analysis of experimental data. As such, we would collect the data from the instrument and we would look at the data and try to do a certain calculation on the data to come up with some meaningful results in which we can actually interpret the results. So part of what we do in this class is after we do the instrumentation and collect the data, we would need to look at the data and try to make some sense out of it so we can become more aware of the observation and what are the things that the data would tell us. So let's say we have a set of observations x1, x2, up to x of n. Could be really n infinite number of data, but of course we cannot collect that infinite amount of data. So there's some limit to this, but it goes from 1 to n. So the sum of the squares of the deviation from some mean value would be according to this formula. Remember, when we are trying to find a deviation, we really try to measure how much would that particular point deviate from the mean to see if we can run the line just simply through the mean, or there are other ways we need to come up with other methods to be able to really capture the best fit to the data. So this is how we can actually do the deviation. As I explained in previous lectures, we simply can calculate the standard deviation, but if you have x1 to x of n number, obviously we can do this. N is the number of observations in this case, and x of m is the mean value. So x of I, x1 minus x of m squared. So then if we wish to minimize the standard deviation with respect to the mean value x of m, we need to differentiate. And we are going to differentiate with respect to x of m because we need to minimize it with respect to x of m. So we take x of m as a variable, and as you know from calculus, you can simply take the derivative as such, and since x of m is the variable, you're going to have minus 2. I'm trying to find this. Okay, there we go. You're going to have minus 2 here. That's a constant. We take the constant out, and then still keep the summation, and then x of I minus n times x of m, since I goes from 1 to n. So n is the number of observation. Then we continue with that. If n is the number of observation, we find that x of m is 1 over n summation of I 1 to n x of I. So the mean value, which minimizes the sum of the squares of a deviation, is the arithmetic mean. So keep that in mind. So let's take a look at the simplest application of the method of least squares. Suppose there are two variables, x and y, and we're measuring these over a range of values. We try to plot x versus y, and we need to measure that. So x could be time versus speed, it could be time versus moment, it could be time versus stress, it could be time versus flow rate. Again, depends on the measurement. So what we try to for the two variables x and y, we try to measure them over a range of values. So we have those data, and we wish to obtain a simple expression for y as a function of x. X and y are dependent. One is a variable, and of course the variation of one depends on the variation of the other. So y is a function of x. The simplest type of function is a linear one. So we might try to establish y as a linear function of a. So as you can see, it's going to be y a sub x plus b. And again, the problem is to find the best linear function for the data. These data could be scattered over a range with different deviations, and sometimes it's not easy to just do that. So we could just plot it and try to find the eyeball it, and then try to draw a straight line through the plot, and that is really a common practice in many cases. But we need to come up with a more reliable mathematical way of doing that. So we seek an equation, as you see, and we therefore wish to minimize the quantity. We need to, again, try to minimize the standard deviation. Again, in this case, it's going to be standard deviation of that function. Then we would set the derivative again with respect to a and b to 0 to minimize that. And then we perform these operations, and the result would be as such. Okay. So we solve these two equations, the one above, the one below it, and we call it 3.27 and 3.28 in the book. Then we calculate a and b as such. Okay, so that was pretty straightforward. Then we need to compute the value of y as y bar. I'm sorry, y hat. Y hat would be ax plus b, and we can do that. And then the standard deviation, the standard error of estimate of y of the data could be as such as shown here. We replace the y sub I hat with the value a sub x plus b, and we get the bottom equation down here, this particular equation here. Okay. Now, the most important, or the more important, and perhaps something that gives us a better estimate of many data that we collect would be to use a quadratic regression. Quadratic regression is used when we have a quadratic function. That is, when we try to determine the higher order polynomial that could fit the data. So we still use the method of least squares, but this method, this regression is called quadratic regression. So we need to differentiate further to determine additional constant. We have three unknown here, a, b, and c. And in order to determine those three unknowns, although they are a constant, but we need to have three equations. So we seek to come up with the three equations so we can solve these three unknowns that we have here. So first, we wish to minimize the standard deviation, so we take the derivative again one by one with respect to a, with respect to b, with respect to c separately. And so we take the derivative of standard deviation one by one. We set that to 0 to minimize the deviation from the mean, right? So we would set that for the following derivatives to 0, and then that would provide us with three equations with three unknowns, simply a, b, and c. Again, we take x of I to the appropriate power, second, third, and fourth, and as such, we should be able to get a, b, and c. We will have an equation with three unknowns, and solving these equations may then lead us to calculating a, b, and c. That's really all that's to it, and it would really help us to be able to solve our problem, which is trying to find the best fit through the data that we have. That brings me to the end of slides. If you have any questions, please feel free to contact me. Thank you.